On September 30, astronomers noticed a faint object on the edge of their survey fields. At first it looked like a minor comet, just another icy body passing through the inner solar system, but when the first photometry came back, the numbers did not fit. The object was brighter than expected for its distance. Its tail stretched farther than the models predicted, and every day, instead of fading, it kept swelling in size and speed. That object became known as Sen-I Phi Atlas, the third interstellar body ever identified inside our solar system. When astronomers track a comet, they expect certain patterns. Sunlight heats the surface, frozen gases turn to vapor, and the pressure from that gas pushes dust away, forming a tail. The more sunlight the comet absorbs, the stronger the outgassing, and the brighter the coma and tail become. The process is slow and steady, but Atlas broke that rhythm. It did not brighten in the gradual curve seen in most comets. Instead, it jumped in bursts. It doubled its luminosity, then steadied. Days later, it jumped again, its coma swelling like a balloon under pressure. The cadence repeated. Observers called them stepwise accelerations. Each pulse was tracked across different observatories. On July, JWST surged. On August, JWST, it did it again. And then in September, the pattern returned. The data showed not a smooth rise, but discrete leaps in brightness and motion. Astronomers know comets can flare, but this was not the same. The flares were too regular, too clean. The intervals measured in weeks, not random spikes. Some researchers compared it to a spacecraft firing a thruster in timed bursts. Spectroscopy deepened the mystery. Most comets show water vapor when they near the sun. Atlas showed little water. Instead, carbon dioxide dominated its spectra. The CDN-10 micron emission line for C or blazed brighter than anything else. In fact, the gas release was 5 times stronger than the water line. That ratio is rare but not impossible. Some comets from the cold outer regions carry more carbon dioxide. But here the balance was extreme, and it stayed consistent with each outburst. Then came the metal lines. Nickel showed up clearly, but where astronomers expected iron, there was almost none. A nickel-jan-rich signature without iron was a red flag. On Earth, nickel and iron appear together in most meteorites because they condense under similar conditions. To see nickel stand alone suggested either unusual chemistry or an artificial separation. Some amateur analysts went further, arguing that the spectral curve matched nickel-cobalt alloys, materials prized in engineering for their strength and corrosion resistance. The growth of the coma was visible even to small telescopes. By mid-September, Atlas's tail stretched over 2 degrees across the sky, wider than 4 full moons laid side by side. Backyard astronomers in Australia reported that the streak filled the field of view, forcing them to use wide-angle optics just to capture the whole shape. The sheer expansion rate shocked observers. Most comets take weeks to develop tails of that length. Atlas was doing it in days. As the sun's heat increased, the object did not crumble. Normally, comets lose fragments as their volatile ices erupt. Atlas held together. Its core remained intact with no sign of breakup. That durability added fuel to speculation. If it was natural, it was built from a composition tougher than any seen before. If it was not natural, then it might be reinforced. Theories of an armored hull began to circulate. The brightness curve added more weight to those ideas. Observers recorded tiny rhythmic changes in the tail's angle, as if it was being nudged. The shifts lined up with subtle increases in brightness, repeating at steady intervals. Instead of random jets firing from the surface, the changes looked patterned. They were small, but across thousands of kilometers of tail length, the coherence stood out. Photometric analysis flagged the changes as micro-thrust pulses. As Atlas closed in on the orbit of Mars, its growth accelerated. By September, a sudden event rocked the tracking networks. Instruments on Mars orbiters detected a shockwave, a pulse of plasma washing across the ionosphere. Data confirmed it came from the same direction as Atlas. Within hours, the Deep Space Network confirmed a measurable shift in its orbit. Something had unleashed energy on a scale equal to nuclear weapons. Yet in space and without debris, the pulse passed Mars without leaving impact scars. The energy moved as a clean spherical wave, not an explosion of rock or dust. That shockwave raised the stakes. A comet can flare, but it does not generate a spherical pulse of energy. The energy release implied control, or at least a mechanism that had not been documented before. Theories ranged from a massive outburst of pressurized carbon dioxide to a deliberate activation of propulsion. Whichever the case, Atlas grew larger and brighter in the aftermath. By the start of October, Atlas was officially classified at magnitude C-dense C, bright enough for binoculars under dark skies. Its tail length had doubled again, stretching nearly 2.5 degrees or 5 times the width of the full moon. Amateur photographs poured into astronomy forums. Some showed the tail spilling out of the camera frame. Others revealed delicate striations, as if the tail itself carried layers of material emitted in waves. Observers compared it to Comet Hale-Gen-Bop, which stunned the world in the late JWST with its brightness and size. Hale-Gen-Bop's coma grew over months. Atlas had matched its visual scale in weeks. Astronomers who specialize in long-gen period comets admitted that the growth curve made no sense under standard solar heating models. In one scenario, a natural explanation involves supervolatile ices. If Atlas originated in a cold interstellar region, its ices could include nitrogen or carbon monoxide, which vaporize at very low temperatures. As it neared the sun, those ices would erupt more violently than water. The bursts could create the sharp increases in brightness. But to sustain those bursts so regularly would require an unlikely reservoir of volatiles arranged in layers. Nature rarely creates such neat pacing. In another scenario, the bursts represent controlled thrust events. If Atlas carries an internal mechanism, then the tail becomes more than debris. It becomes exhaust. The carbon dioxide could serve as propellant, vented at precise intervals to adjust trajectory. The lack of iron but presence of nickel might then mark engineered material, designed to withstand stress and corrosion in deep space. As Atlas grows faster, so does the speculation. Observers track its speed with each passing week. Its acceleration exceeds what gravity alone explains. Outgassing can add push, but the vector of the acceleration matches better with deliberate thrust than random venting. Each measured step lines up with a brightness spike. Each spike lines up with a color shift in the coma. The evidence stacks in layers, one atop the other. The blackout window now looms. From October Bar-TH to Shabathi-8, Atlas will pass too close to the Sun for Earth-Jan-based telescopes to see. During that period, it will reach perihelion, its closest approach, where heating and activity should peak. Instead of observing its most critical moments, astronomers will be blind. The geometry of the blackout means that if anything dramatic happens near perihelion, the record will depend on spacecraft or amateurs with improvised equipment. Some agencies have quietly instructed their teams to halt high-gen resolution imaging during the blackout. Internal memos reference security reviews. Proposals for radar mapping were rejected without public reason. That has only fueled suspicion. If Atlas behaves in ways that cannot be explained, the official data may never reach the public in real time. Independent groups have begun pooling resources to fill the gap. Distributed telescope arrays share raw images across encrypted channels. Amateur radio astronomers plan to monitor for plasma bursts, hoping to detect echoes of another shockwave. Backyard telescopes across both hemispheres prepare to log every flicker until the sun swallows the view. The grassroots networks may be the only ones recording what happens next. The growth of Atlas is now the centerpiece of nightly discussions among astronomers. Its tail stretches across constellations. Its brightness climbs faster than models can project. Its activity defies smooth physics, instead arriving in measured bursts like a clock. Each new dataset forces researchers to choose between two unsatisfying explanations: a natural comet with behavior never before seen, or an engineered body making controlled maneuvers near the sun. As Atlas draws closer, the scale only intensifies. Photometric models suggest its current energy output is on the order of 10 gigawatts, comparable to 10 nuclear power plants running at once. That is not energy generated by a machine, but energy released through volatile venting and solar heating. Yet the scale is so large it invites comparisons. The Sun is pumping unimaginable amounts of heat into Atlas. The way Atlas channels that energy sets it apart. Instead of tearing itself apart in chaotic eruptions, it grows, steadies, then bursts again with precise timing. Observers note its resilience. Comets of this size and brightness often fragment before reaching perihelion. Swan, another object inbound at the same time, is even larger and shows signs of an armored composition. Atlas, though smaller, behaves like a craft maneuvering in formation. One looks like a fortress, the other like a drone. Both arrive within weeks of each other, their perihelion distances within 50 million kilometers. The odds of such synchronized arrivals are astronomically small. The more Atlas grows, the more the comparisons feel inevitable. Astronomers cannot dismiss it as routine. Its spectrum is wrong. Its acceleration is wrong. Its bursts are wrong. And yet its growth continues at a pace no natural body has matched in living memory. The updates now come daily. Each night the comet brightens, each morning its tail extends farther. It is not slowing down, it is not breaking apart. It is growing faster, expanding into one of the most visible, most anomalous objects to ever cross the inner solar system.